Welcome to this video that provides an introduction to the characteristics of human environmental exposure data. Now I want to talk briefly about censored data. Censored data, that term just refers to observations in distributions of data, measurement data, that are special. And those observations are special because they are non-quantified amounts or non-quantified concentrations. That occurs when the abundance of a contaminant in some medium is lower than the sensitivity of the method used to measure that contaminant in that medium. So if the amount in the sample is lower than the sensitivity of the instrument, then you cannot detect the presence or confirm the absence of that substance from that medium. In general terms, that event, right, or that called a non-event, is often called a non-detect. The result of that sample was a non-detect. So that can happen, right? In fact, it's very common for the lower end of environmental exposure distributions to contain non-detect values. Now, that limit of detection or the sensitivity of a measurement method, it depends on many factors, and going into those factors is beyond the scope of this class and this talk. But you can think about some of the major influences are, well, how much of the media was collected, and of course what's the concentration of the substance of interest in that medium. Also important is how responsive the laboratory instruments are to that substance of interest. And another important factor is how reproducible repeated analyses of the same sample are. Right? The more reproducible, the more precise, generally the greater the sensitivity, right? The greater the ability to detect low amounts. So for an introduction to some of the key topics around sensitivity, I suggest reading this article in the Synergist, which is a monthly magazine published by the American Industrial Hygiene Association, for a more in-depth review or more in-depth description of sensitivity and related characteristics. I recommend this paper. It was published a few years ago by some scientists that many of us here at the school know and work with from time to time, who are at the Silent Spring Institute. So I recommend taking a look at this paper. This slide contains a table from the first reference or citation on the prior slide, and the table on the right is reproduced from the second publication noted on the prior slide. I ask you to read each of these tables in your own time. I think that would be useful. But what I want to point out is some of the main concepts which appear in both tables, even though the terminology is somewhat different between the two tables. That the basic concepts conveyed by each table are this: that there's first concept is one of detection. So a measurement method may be able to detect the presence of a substance of interest above the quote noise in the sample, above the kind of the baseline of a measurement method. But that signal that can be detected with confidence as being greater than the mean, greater than the noise, could be insufficiently high to actually quantify. It'd just be like, oh, I heard something, but I don't know what direction it came from, or I don't know how loud it was, or the tone or the notes of that sound. That's like orally, listening. That's what I just described as hearing something but not really being able to like get a sense of direction, for example, is analogous to being able to detect the presence of a substance in a sample, but not having enough of it detected to actually quantify how much was there. So that's detection limit. The next limit is quantitation limit. The signal is larger than just enough to detect. In fact, it's enough to quantify the amount present with confidence. And that confidence can often be expressed like a statistical confidence based on repeated results from different types of quality control sample analyses. And then the third is method reporting limit, or reporting limit. This would be the amount that the instrument can detect, the instrument can quantify, and it's also an amount that's greater than the amounts you find in samples that you expect to be free of the substance of interest, so-called blanks. Ideally, you don't find the substance of interest at all in blanks, like pure water, let's say, as a blank or highly distilled water as a blank for analyses of lake water or river water or blood serum even. So ideally the blanks will have return no signal, but sometimes that's not true. Sometimes the substance of interest is in the blank, and obviously you if that's true, you can't be confident that a response in a sample of about the same magnitude or lower than the amount in a blank is a true response. It simply could just be due to the same factors that cause the presence of that substance in the blank. So method reporting limit. So those are some common concepts and terms, and to learn more about them, again, I encourage you to read these two articles. Here's an example from a paper. This is our older paper, 1996 publication, that's summarizing the measurements made by the U.S. Food and Drug Administration of about 10 different compounds in foods collected as part of the FDA Total Diet Study program. It's a food quality surveillance program conducted by FDA on a regular basis. So what's shown in this table is a limit of quantification in the second column from the left. It's in parts per billion. So the limit of quantification for arsenic in these samples is 20 parts per billion. 20 parts of arsenic per billion parts food. That's going to be solid to solid, so that ppb is going to be analogous. It could also have been micrograms of arsenic per kilogram of food. So that's the LOQ. You see the LOQ for cadmium was a little bit lower at 10. For lead was the same as arsenic. Get down to some organics, chlorpyrifos, diazinon at 3 ppb, all the way down to an organochlorine insecticide called lindane was 1 ppb. So the LOQ is not the same for every substance. That's important to recognize. You can see here the NTDS is the number of foods, so it's the number of foods in the total diet study that arsenic was not quantified in. So 97 out of a total of 146 foods that were analyzed, arsenic was not found in. So 2/3, right? Cadmium, 105 foods did not contain a quantifiable level of cadmium out of 203 total foods. So you can see this is one way this LOD is used. It's to describe the relative frequency or the absolute frequency of detection. So what to do with these non-detects when analyzing data or summarizing data? Well, the general approach is to impute a value for the censored or non-detect observations. The EPA's 2019 update to its guidelines on exposure assessment, section 5.3.3, it's a couple pages long. It's similar to the two other reports that are cited in this deck, but I think it's worth taking a look at too, because it talks specifically generally about approaches to imputing a value for the censored observations. That document describes three basic approaches. One is termed simple substitution methods, and these are commonly used, I can tell you, in practice. Perhaps the most commonly used is imputation method is to simply divide the reporting limit by 2 and use that value, the reporting limit divided by 2, as the imputed amount or concentration for each censored observation. A very similar approach is to use the reporting limit divided by the square root of 2. Some people argue that this geometric kind of approach is superior to simply dividing by 2, but really, that's, in my view, that's an esoteric difference. And what's more important is to impute a value and be transparent about the value that you did impute. Another approach is to use the reporting limit rather than dividing by 2 or the square root of 2. Of course, that's going to bias those observations high, because the whole notion of the reporting limit is to indicate that the amount in the substance is less than the reporting limit. So if you impute with the reporting limit, of course you're going to be biasing those observations a little bit high. Alternatively, you could impute a value of 0, but that's going to introduce low bias into those observations. You could also consider omitting those observations entirely. So now that's almost like imputing a value of 0, but you also remove that observation from the data set, so your sample size is smaller. These simple substitution methods like these are used very commonly. Another approach is a distributional method, where you fit a distribution to the quantified observations, and then you assume that the lower or censored part of that distribution applies to these measurements. And because you can impute because if you know the distribution parameters, like the geometric mean and the geometric standard deviation, you can estimate, say, the 10th percentile, the 5th percentile, the 1st percentile, even if the measurements themselves were non-detect. So that's what the distributional method is. The robust method is similar to the distribution methods, but it differs in that it assumes a distribution only for the non-detect values. I refer you to the literature to learn more about this. An example of its application is in this paper by Cindy Hu and co-authors, including Jared Liddy, who I think you all know too. But regardless of the method, what's important, one thing that's always important, is to understand the sensitivity of the results and the conclusions of your analysis to how the non-detects are treated. Right? You don't want the treatment of the non-detects defining or determining the conclusion of your analysis. That would be a flawed analysis.